So this is like 20th time recording this. Yeah, we're gonna get started. I haven't been logged in for the past few millennia, so we're trying to get back into the old calculus mountain, whatever. I don't even know what I'm trying to say, but yeah, we got to start off with chapter 13 now. I pulled a few all-nighters to get to chapter 12 because I'm like months behind in my class, but now we're back. Well, not really. I'm still like a few weeks behind, but we're starting back with chapter 13. So I guess I picked up on a good spot. So we're gonna dedicate some time to this. Hopefully have a fun time. Yeah, we're starting off with chapter 13, functions with two or more variables. I didn't really want to do it alone, so next best thing would be to return to the channel that I left like 5-6 months ago. So should be exciting. So to start, I downloaded the lecture, so we'll just pick off. I know that the main difference between calculus 1 and 2 is probably the fact that we're in 3D. So I guess that makes sense. Yeah, okay, up until this point we've been dealing with single variable functions, which really means that there's one independent variable, x, and the value y, which is dependent on the value of x, so y is the dependent variable. Yeah, I mean, it's a standard xy axis. But I guess now, well, this y equals f of x, the domain is a set of x values, which means it is a subset of the x-axis. What the fuck is that? Domain is a set of x values, which means it is a subset of the x-axis. What the fuck does that mean? Maybe if I read on it, it'll make sense. In 3 space, we have two independent variables, x and y, and the dependent variable z. Z equals f of x and y. So the domain is a set of points x, y, which means it is a subset. Okay, that makes sense. So depending on what points you pick, it's going to be a set of points that belongs to that xy plane. So I guess I could probably draw it out. So I guess for example, if you're given an xy plane like this, right? This would be your x, this would be your y, this would be your z. What I'm assuming it's trying to say is no matter what set of values that you pick, whether it be for example 1, 2, or 1 and 2, for example, if I were to pick f of 2, 1 or f of 1, 2, the points that you're picking, the domain is a set of points that belongs to that entire plane. So in a standard xy graph, for example, the domain, the point that you're picking for the y to depend on, is going to belong to that axis. So like I said, on an xy plane, no matter what point you pick, it's going to lie on that x-axis, which would therefore mean that it is a subset of the x-axis. And in 3 dimensions, I'm guessing you could span that. So instead of just being, for example, a subset of the x-axis, here it's a set of points that belongs to the entirety of that xy plane, which would then mean it's a subset of the xy plane. 4 space. What the fuck? In 4 space, we have 3 independent variables, x, y, z, and an independent variable, w. W equals f of x and y and z, so the domain is a set of points. Okay, I guess okay, wait, never mind. I guess I was thinking there was a 4-dimensional plane, and I was I didn't think we were getting to that point. But I'm guessing what it's trying to say is that you can kind of stretch that. So given a set of dependent variables, the domain is going to be a subset of that specific space that is created by those dependent variables, I guess. Okay, so let's advance. I guess that makes sense. I guess that makes sense. Let me just write a brief note of that. I don't know what the fuck I was reading at the beginning there, but sure. Chapter 13. Functions of 2 or more variables. Now, I hope none of you are watching this with the intention that I'm going to be teaching you anything. I don't know what the fuck I'm doing. I've been meaning to write notes for a while, and I feel like this is a way for me to stay consistent and somewhat accountable. So that's what I'm doing this for. But okay, let me just write a brief note. So given y equals f of x, the domain is a set of x values. Thus, a subset of the x-axis. This same logic can be kind of spanned, like I said, to y is equal, z is equal to f of x and y. The domain is a subset of the xy plane. So that makes sense, right? That makes sense. Okay. So we should be able to identify domains and represent them graphically in 2, 3, or 4 space. We cannot draw the domains for a 5-space function because it is a subset of 4 space, and we live in a 3-dimensional world. So I'm guessing the reason why we can draw the domain of a 4 space is because the domain of a 4-space like function would be 3 spaces, and we do indeed live in a 3-dimensional world, so I guess the domain would just be everything. For 3 space, it would be a plane, xy plane. So in class, we will go over how to determine and graph or describe domains. For now, we will go over some simplified domains. So I didn't go to that class, so I think I'm fucked for that specifically. Which, it is what it is, you know. We'll figure it out. Here, let's read on with this. First, let's start with reviewing 2-space functions. So I guess this is kind of easy. So this will be like a subtopic. So 2-space. Let's do this. So it's going to give us a function. So f of x is equal to, in this case, 1 over x plus 2. Obviously, we know that the denominator can't be equal to 0. So x can be really any value except for negative 2. If you want to draw that in interval notation, it's pretty simple. Union, negative 2, infinity. Because we can't include that negative 2. And we can include any other point but that negative 2. Right? So domain's pretty easy for that one. As far as 3-space goes, we'll see how they do it. I'm not too sure how the domain's going to be looking for that one. Let's see. So it's giving us some f of x comma y. Now what I have to remember here is that it takes in x and y. Obviously working with 2-space, you're going to be like, oh, it only takes in x, and I guess I don't really want to make the mistake of doing that. So in this case, x plus 2y over x minus y. So this is probably going to be more complicated because x and y can't cancel each other out, because if they do, like for example, if I chose the point like 3, 3, right? 3, 3, x equals 3, y equals 3, they would cancel out. and would give us 0 in the denominator. So in this case, it says that x minus y can be equal to 0, which is correct, and x cannot be equal to y. They get this from this, obviously. It's like a direct, it's like common sense. I'm saying that because I didn't know. I was like, where'd they pull that from? Well, they just kind of moved it to the other side. So yeah, not that difficult. In this case, the domain, it's a little interesting notation, but it's essentially saying that the values of x and y where x cannot be equal to y. So it's saying that the values of x and y whereas x cannot be equal to y. I guess they kind of write it the same way here, but this can also be the values of x where x cannot be equal to 2. And this one's actually fairly intuitive. I mean, it's the values of x and y where x can't be equal to y. So I guess that makes perfect sense. Let's continue. For space. So I wonder what application is there for physics, for example? Like, what the fuck would be the fourth dimension in physics? Who knows? Who knows? So for space. In this case, we're going even fucking further. Our function now has x, y, and z. Next thing you know, we have the whole fucking alphabet. So we have some function where it's 1/2 minus x plus y minus z, where again that denominator really can't be equal to 0. Where 2 minus x plus y minus z cannot be equal to 0. Now how are they going to write that? The domain, whereas where the values of x, y, and z value, the domain is, or how is it read again? Domain that contains the points x, y, and z, where x minus y plus z minus 2 cannot be equal to 0. Okay, interestingly enough, it's saying that this is the entire XYZ space with the exception of the plane x minus y plus z equals 2. Which I guess makes sense. I don't know. I do know that the point normal form of a plane is going to be in this form where x, I'm pretty sure this is the formula of like a plane. So I guess that would make sense. So like, for example, if I were to move that y over, so it'd be y minus 2 plus z equals 2, for example. This is a plane. This is a plane, right? So it's saying that it can be any other plane except for this. So I guess that does make sense, actually. That does indeed make sense, because this is in the formula of a plane. So if yeah, I mean, I don't know what to say. That makes sense. So that's domain. Jesus Christ. You will be graphing functions in 3 space, which you've already done. Remember the quadratic surfaces? Yes, I do. Do not fucking remind me. Those took forever. So, example, f of x comma y is equal to x squared plus 3y squared. This is an elliptical paraboloid. Yeah, totally. Totally. Which I guess makes sense, because if you do traces, like if you do the zy axis, it's going to be a parabola. If you do the yz axis, the xz, I mean, is it the xz and the yz axis? Those are both going to be parabolas. So I guess that makes sense. If you were to do the z axis, for example, that would be a, I don't know if it'd be a circle, but it'd be something round. I don't know what to say. But yeah. So rather than graph the surface itself, we would like to represent the 3D surface on a 2D plane. Why? Rather than graph the surface itself, we would like to represent the 3D surface on a 2D plane. To do this, we must determine the equation of a level curve. What the fuck is a level curve? Oh, look, yeah, what is a level curve? It's the intersection of a plane parallel to the XY plane and surface. So it is a trace. It is a trace. We did do that. The difference is we look at the traces parallel to all 3 coordinate planes. For a level curves, you only look at those parallel to the XY plane. Okay, that makes sense. The traces that we did, we would take multiple different planes. We would find kind of those traces would be, the traces would be parallel to those coordinate planes, and then we would use that to kind of look at the bigger picture and graph the entirety of the quadratic surface. But in this case, for a level curve, I'm guessing it tells us we only look at the XY plane. So we're running a plane through the surface and forming a curve. That's that does make sense. We're literally just yeah, okay. So here it's giving us some little elliptical paraboloid where z is equal to f of x and y. That z is some height k from the origin, or where z is equal to 0. So that height right here is k. Once we get that plane that's parallel to x and y at that height k, it's going to give us a level curve of height k, where f of x and y is equal to k. Now, where's the application for that? Once we find a few level curves, we can put them onto the xy plane, and the result is a 2-dimensional representation of a 3-dimensional surface, and we call this a contour map. That's actually really fucking cool, I'm not gonna lie. That's actually really cool. So, yeah, I'm not gonna lie. I was trying to hate on it, but that's actually really fucking cool. So using these level curves, using different heights, we can kind of map out a 3-dimensional surface on a 2-dimensional plane. That's fucking cool. I said 2-dimensional plane like a plane isn't 2-dimensional. I mean a 2-dimensional, like, just a 2-dimensional representation. Forgive me for my language. Whew. Okay. Sorry. Whenever I have energy drinks, it kind of just like thirsts me. Also, this is entirely random, but you guys should listen to this album. It's called The Flying Beagle. It's really fucking good. Sorry about that. Let's continue. I just kind of wanted to get that off my chest, but yeah, kind of makes sense. Contour maps. Okay. Here's some examples. So here are a bunch of level maps that we've taken. I'm just kind of giving us a perspective of how it would look. So it's pretty cool. This is what it were to look like on like a plane. So pretty cool. I think this is like a heat map or something. I feel like I've seen these before. This is also pretty cool. This is literally just a big hill. That is this. That seems really useful. The first example represents the height of a surface by labeling each curve with the corresponding height, which is the z value. Kind of like what was happening here, where you would take different k's and kind of like line them up to kind of show like an accurate representation of a 3-dimensional surface. The second one uses colors and an index to show the heights, which honestly I prefer because it just looks cooler. The way the curves are spaced out is important. Notice if you look at the contour map and see where the curves are tighter together, -4, -5, 4, -5. What the fuck are you talking about? Where the curves are tighter together? Huh? The way the curves are spaced out is important. Where's 4, -5? I'm confused. I don't know where that is. Are you talking about here? Or here? I think here, no? I'm guessing it's saying where the curves are tighter together, so like around here, I'm assuming. Literally, what the fuck are they talking about? I'm so confused. 4, -5 is like, where does that appear? I don't know where that appears. I'm kind of like just staring, hoping for something to pop out at me, but I'm not seeing much. Do the same for the curves or spaced out further apart. What do you notice about the steepness of that surface? I'm guessing the... I don't know. Oh, I'm a fucking idiot. It doesn't mean negative. It's mean 1s to 2 versus 4 to 5. I'm a fucking idiot. Okay, so looking at 1 to 2 compared to 4 to 5, 4 to 5 is obviously steeper. So duh. Like, okay. I'm guessing that's what they wanted. That's what they want us to see. Given the curves are tighter together, it would insinuate that it's steeper, which makes sense. I don't know what to say. Yeah, it makes sense. Yeah, that makes sense. If you haven't figured it out yet, we'll discuss in class. That would have been me, but not. We see contour maps all the time. Map of the US appears with a bunch of curves and lines. That is a contour map. How do we determine the equation of a level curve? Since the curve is an intersection of the surface with the plane, we set them equal. For example, okay, that's actually a pretty good example. We'll call this one level curves. Level curves. Here we got a nice example. Holy shit. So given like some surface, right? In this case we get z is equal to x squared over y squared, whether y is not squared. Here we're trying to find the intersection with the plane y is equal to 2. That is not what we're going to do. Z is equal to 2. So you can imagine kind of like... So like a... What the fuck am I trying to do? So you can imagine here, my thumb is the x-axis, right? We're trying to find the plane that's 2. So that entire... like area, this is the x and y, right? X and then the y. We're essentially finding the plane, or z is equal to 2, and finding that intersection with this like surface, I guess you could say. So in this case, the way that we find this intersection is we just set them equal to each other like it says. So where 2 is equal to that x squared over y. If you rearrange it, becomes y equals 1 over 2x squared. And this is what it would look like. This is what the level curve would look like. In this case, it would be like a really stretched out parabola, I guess. I don't know. It would be some stretched out parabola. So I mean, that's not too bad. That really is not bad. I mean, it's pretty interesting. I guess here's where the really bad stuff happens. But this, I think this is just 12. I think she messed up. That's 13.1. I think this is 13.2. We're finally doing some calculus. We're finally doing some calculus. In this case, we're finding limits. So it's saying it's easy, but I don't know if I trust it. We'll see. I don't want my Siri's acting up. I didn't call for you. Alrighty, so let's get started on this. I have to finish a book by tomorrow. I'm like 10 pages in. So after this, I'm probably going to read. I wonder how long it's going to take me to finish this, actually. We only have... Oh, we're basically almost done. I'll do some examples and that'll be it. Yeah. Okay. I think finding limits in 3 or 4 spaces is relatively easy. Pretty much works like limits in 2 space. Just plug in and hopefully you get a result. What the fuck you mean hopefully? I want to get a result, but what do you mean hopefully? Like if I don't, what happens? Only thing is with limits, I hate writing the whole limit as x. Like I feel like I'm drawing half the time. Like there has to be some easier like syntax for this shit, right? So limit of x comma y as they approach 3 comma 1 of, Jesus Christ, this one's writing x y minus 2x squared is equal to 3 times, I guess here's just actually plugging like direct substitution and just fuck it, hope it works. 2 times 3 squared. Value of this exists, so I'm guessing this is what the limit would be equal to in this case. I'm guessing it's going to show us one, yeah. It's going to show us one where it doesn't work, so the limit of x comma y as that approaches 0 comma 2 of x plus y over now y minus 2. Using direct sub, we get that 0 plus 2 over 2 minus 2. And then here we get an issue because you can't have a 0 in the denominator. It's not good. Yeah. That's not good. So this is equal to 0. Or infinity, I mean. So here we got a problem. Indeterminate forms are a problem. They're not good. It's really not good. I wonder what they're gonna do. Then there can be 2 cases. One where you find the limit by manipulating the original function, and the other where you suspect the limit fails to exist. This one takes extra work. If it takes extra work, I don't want to do it. If it takes extra work, the limit could solve itself, you know? I don't care. Let's see. Let's look at the first case. So in this one, it gives, we get an indeterminate form again. 0 over 0. So, okay, so let's make this indeterminate form. So in this case, the limit of x comma y as it approaches 2 comma 1 of x plus y over now I'm drawing the wrong fucking one, 2x minus 4y over x squared minus 2xy. When you plug that in, I'm going to trust them. You get 0 over 0. We cannot use L'Hopital's. This looks horrible. We cannot use L'Hopital's. La Hospital, which isn't good. I like La Hospital. La Hospital brought me through calculus BC last year, so it's a bit sad. Whatever. We can factor. We can manipulate via factoring. So in this case, it's kind of equivalent. Well, we can factor out a 2, and we could factor out an x. So it's essentially the same thing as just doing the limit of x comma y, blah, 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 2 comma 1, of now 2 times x minus y, or 2y rather, over now x times x minus 2y, right? And since we have cancelable thingamabobs, you cannot cancel that. It's kind of the equivalent of just saying x minus y as you approach 2 comma 1 of 2 over x, strictly because these would then cancel out, right? Making life 20 times easier for us. In this case, this is solvable, and we get a very tedious answer. We get 1. So that's great. Really, these have been really. This is pretty intuitive. This really isn't that difficult. Okay, I say that. Where we run into problems, as your fucking 20-page essay, is where we can't manipulate. So what does this mean? It probably means the limit does not exist, but how can we show this? How can we show that the limit doesn't exist? I thought you could just say it doesn't exist, and then that was it. Well, no, because if it's indeterminate, then you don't know. Okay. Back in Calc 1, when was the limit DNA? It happened when the limit from the right and the left were not equal. Here's your problem. In 3 space, you can approach the point from an infinite number of directions. Well, that's fantastic. That's really fantastic, actually. It's really amazing. I guess that makes sense because given limits, right, in calculus 1, left and right on the x, because that's where you would approach, right? You would approach it from the x and from both directions. But in this case, we can approach from the y too, and all of the different fucking directions. So that's fantastic, actually. So you must show that at least one of the paths to the point produces a different limit than one of the other paths. So the first 1,000 paths can produce the same limit, but the 1,000th and first might be the one that is different. Let's hope we are luckier than that and we stumble upon 2 different limits in the future. What the fuck? So I have to just like have a dice roll and just kind of determine which one. That's great. That's really great. That's really, really great. Oh my god. First we will look at the path. X is equal to 2. We will replace every x with a 2 in the limit. What? I'm confused. Oh, I'm an idiot. Okay, yeah. When you do x, you get 1/2. Now let's look at the path. Y equals x plus 1. So here we're going to replace every y with a x plus 1. When we do that, we get the limit as x versus x and y is approaches 2 comma 3. We get 2x minus, so we get 1. So we can replace both x and y. If we replace x with the x plus 1, we get a different value than if we were to do x equals 2. So that's pretty cool. I'm a little confused. So this is just all we do then? If it's indeterminate, we fucking pick random. It's so windy outside. So we just pick random points or random directions to come from. And if they don't line up, doesn't exist then. Great, we were done the past produce different values, so we have shown the limit does not exist. If the results been the same, we'd have to keep trying other paths until we found that it's different. Well, that's fantastic. That's really cool. That's really awesome. So, okay. Let me just write a quick note. I'm not going to write all that. In 3 space, to show a limit does not exist, we must find 2 directions that get a different value. At least it's only 2. I mean, it'd be more annoying if we had like fucking 20 or 3 or whatever. So I guess this really isn't too bad overall. So a quick run through. We started off with finding the domains. I mean, which is pretty simple. 2 space, obviously, we're just looking at the x. So we're looking, the domain would be a subset of the x-axis. In this case, we already know how to do it 2 space, so I'm going to go over that. 3 space is a bit more different. We need to find where that denominator is 0. In this case, it's 1x minus y equals 0, which is 1x is equal to y. So the domain would be the points in which it's points of x and y where x is not equal to y. 4 space, it's a bit more difficult because we have 3 different variables to look at. In this case, the bottom just can't be equal to, in the case, the bottom 2x minus y, 2 minus x plus y minus z cannot be equal to 0. If you rearrange that, we'll rearrange after. The domain would be the values of x, y, and z, where x minus y plus z minus 2 is not 0. In this case, on a more graphical like representation, right, it would be kind of like any value, so long as is, wait, was it, yeah, it was the entire xyz space with the exception of that plane, right? X minus z plus z equals 2. So every value that's not in that plane, I'm assuming, right? With the exception of that plane. That's because that's a singular plane. Yeah. We could actually find the normal vector of that plane. I'm not gonna do that, but it's just the coefficients of the x and y and z. So after that, we have level curves, which is actually the coolest part about this. Here we just take a parallel plane to the x and y at some height k to kind of like map out a 3D function in 2 space. Which honestly, I can't even lie. This is actually really cool. They make these things called contour maps. I personally think this one's my favorite. I like this one. I like all the colors. But yeah, that's great. You just label each curve with the corresponding height, whatever z value you pick. The more spaced out, the less steep they are. The tighter they are, pause, the steeper it is. That's pretty cool. And we have how to actually find the equation of a level curve. So we kind of just set the z to whatever height we pick. So for example, if you want to find the level curve at like z equals 2, that right, like that height k is equal to z is equal to 2. Kind of just plug that into the surface, and it'll give us some. We're basically taking that z plane and mapping out the x and y, like what that graph would be on that plane. So in this case, we get some parabola. As far as limits go, we can obviously get it through direct substitution. Evidently, you could always go that route, except you could get a value that's indeterminate, or a value that just simply doesn't exist. In this case, where we get 0 over 0, no La Hospital, unfortunately, but it's kind of sad. I like a hospital, but we can fix it through factoring. which is kind of the same as you would in like calculus 1, for example, kind of like manipulating that function to find the behavior. If you can't do that, that's where things get a little crazy, because then we just got to look at multiple different paths to see if you inevitably get a different value. In this case, we approached it using x equals 2. So we just replaced every x with 2 in the limit. Yeah, okay. So you replaced every x with 2. And then we did add the path of y equals x plus 1. So we're not exactly manipulating what direction we're coming from. We're just like picking values to look at different paths. So the first one's just x equals 2. The second one's like y equals x plus 1. And you get 1/2 and then 1. Obviously, those are different. So the limit as you approach y is equal to 2 and y is equal to 3, you get different values, so the limit doesn't exist. If they are the same, you kind of just got to keep trying it out. Keep trying your fucking luck. So that's it for chapter 13. Really not that bad. Not really that math heavy. It's pretty conceptual. I guess it's trying to just show that overlap between calculus like 1 and calculus 3, for example. Really not bad. I'll be making another one of these for the next few chapters. Let me actually see. This was 13.1 to 13.2, so not too bad. Let's see. After this, we have let's see. I guess this goes deeper onto contour maps. I guess it's just gonna show like a bunch of contour maps. I don't know what's gonna do. Listen, this is fucking cool. I actually I really like the contour maps. I really like these. Only thing I'd hate about this Blackboard bullshit is that it like removes you completely from whatever you're trying to look at, which I don't like. Now, after this, we're gonna be looking at partial derivatives. I don't know what the fuck a partial derivative is. Oh, it's these. I actually kind of like the little whoosh, whoosh. It's gonna take a bit of getting used to, but yeah, it's pretty cool. We're gonna be going over this next. I'll be bringing you guys through the journey. But yeah, that's it for this one. I'll be seeing you guys on whatever other one we're doing, I guess. So yeah, thank you.